let's cover the services a particular layer is offering to the layer just above it. So in this context, there are few terminologies. The first terminology is entities. So entities is nothing but the active elements in every layer. So this could be a process, this could be an intelligent IO chip. A process could be something like the process of data transfer, which can have a child process also. Then there are peer entities. Peer entities means entities in the same layer on different machines. We know that the entire operation of the OSI model is on a peer-to-peer basis. So that means a particular layer which is doing some kind of functions at the transmission machine, the destination machine, the same layer will have equivalent functions. So it's called as peer entities. So peer entities, they are the responsible for application to application or the process to process mapping of the services on the networking environment. Now, what is a service provider? We know that every layer is giving service to the layer which is just above it. So if a service provider layer is layer N, then the layer N will give service to the another layer which is at layer N plus 1. So a service provider is N and the service user is N plus 1, the layer just above it. Now what is the service access points? So service access points which lies at the interface of these two layers, and those layers are the layer N, which is the service provider, and the layer N plus 1, which is the service user. So while describing the services in the OSI model, we need to have these terminologies in mind which I just described. The entities, which are nothing but the active elements in every layer. Every layer will have different entities depending on their functionality. Peer entities are the entities in the same layer on different machines, different hosts. Service provider, for example, if it is layer N, the service user will be N plus 1 because layer N will be giving services to layer N plus 1. And the interface in these two layers is called as the service access points. We have seen the two kinds of services are possible in the OSI model. The connection-oriented services. These are the services before data is sent. The service from the sending computer has to establish some kind of handshaking with the receiving computer. So unless this handshaking is done successfully, the actual data transfer won't start. And therefore, in case of connection-oriented services, the handshaking between two machines are important. The synchronization is important. Once these issues are addressed, then the data transfer will commence. So that is connection-oriented kind of services. So what is connection-less services? So here data can be sent at any time by the service from the sending computer. So no need of synchronization. It is assumed that the receiver machine is ready and the data is sent irrespective of whether the machine is ready or not. There is no, in fact, indication from the other machine, other host, but the data transfer takes place. So that is connectionless services. Now, I just appeal to the students, just ask yourself, whenever you download a music file from the internet, whether it is a connection-oriented service or connectionless service. Just try to browse, just try to go through the book which I referred, the Tannenbaum book, and then try to answer this particular question. And you can also answer this question whether email is a connection-oriented service or connection-less service. So if you are thorough with what I am trying to deliver, then you will be able to answer both the questions. The concept of service primitives we have already seen, and there are four kinds of primitives: the request, the indication, the response, and confirmation. These are the four service primitives. So request is an entity wants the service to do some work, that is request. What is indication? Indication is entity informs about an event, a certain event is happening, and the indication is given by the entity. So that is indication, one of the service primitives. What is response? Response is the entity responds to an event. When a certain event happens, there is a response from an entity. So that is response. And once the request is done, then the confirmation has to come from other entity. So that is confirmed. So in the OSI model scenario, you will find these 4 service primitives, which is request, indicate, response, and confirm. So here you can see there is a sending computer and receiving computer. So transport layer of the sending computer, the hub of the OSI model, will deal with the transport layer of the receiving computer. So it is as if they are got peers, and therefore they will have equivalent functioning. So whatever is happening here, the reverse process will happen here by the receiving machines. The same is the case with the networking layer. So here it is shown that a certain request is, here you can see that both the service primitives, there is a request, the transport layer is making the request from the network layer. The confirmation is given by the network layer to the transport layer. The same way, there is an indication about an event by the network layer to transport layer, and in addition, in response to this indication, there will be a response from the transport layer to network layer. So this is the relationship between the service primitives. Now in the networking scenario, we often discuss about bandwidth. So what is basically bandwidth? It is the capacity of the medium to transmit the data. And in case of, if you describe the bandwidth by means of analog means, then it is measured in hertz or cycles per second. If you describe the same thing in digital scenario, then it is measured in bits per second, BPS. So it's like Mbps or Gbps and so on. And accordingly, the networks are called as giga networks or mega networks and so on. This is the, again, concept of bandwidth, which measures the speed, roughly the speed of the network. So this is how it happens. The framing part, the physical layer will be dealing with only bits. The data link layer, every layer will add a sort of information when the data is transmitted or parsing through that particular layer. So this is like bits, and then the data link layer will be adding a certain value to this. The network layer will again add certain value to this. Again, transport layer will add its header to this. The session layer will add header to this. The presentation layer will add header to this. Application layer will add header to this, and ultimately the data will be passed on to the user. So this is the sort of hierarchy which is followed in the OSI model. So as far as the physical layer is concerned, we have already seen that the signals are important, the transmission media is important, whether the transmission is going to be analog or digital. So these two things are important, and what kind of transmission and switching, so that's important. So the signals, basically they can be analyzed by using Fourier analysis, and this Fourier analysis, it's a mathematical tool, and by using this mathematical tool, a periodic function can be constructed, can be expressed as an addition of number of sines and cosine functions. It's a very, you must have studied this in digital communication, but a basic mathematical tool which will be used for analyzing the behavior of the signal in the noisy environment. So it deals with the fundamental frequency and its harmonics. Fundamental frequency is the frequency which is basically the frequency of the signal, and harmonics are nothing but the integer multiples of the fundamental frequencies. And we often heard here what is baud. So baud is nothing but the number of signal level changes per second. So all this matters in the Fourier analysis. And in this physical layer, the another thing which is important is the maximum rate of data transmission. So it is governed by something called as maximum data rate of a channel, which is generally expressed by using Nyquist. Nyquist is the name of the scientist who has pioneered this particular theory. And the maximum data rate, the The data rate which we can have at the most on the network is expressed by 2h log v to the base 2. Often it is expressed in bits per second, where h is the line bandwidth and v is a signal with discrete levels. So this is generally a calculation. For example, a noiseless 3 kHz channel cannot transmit binary signals at a rate faster than 6000 bps, because if you just do this calculation, the 2 into h is 3 kHz, so 3k log of 2, because there are two levels to the base 2, it comes out to be 6000 bps. So you can't have a maximum transmission rate higher than 6000 bps. So that's the ultimate rate at which at the most the signal can be transmitted over the channel. And this is given by Shannon's theorem. The maximum data rate, which is expressed in bits per second, which is given as h into log of 1 plus the signal strength divided by noise strength, basically signal to noise ratio, to the base 2. Okay, so for instance, if you want to calculate a 3 kHz channel with a noise ratio of 30 dB, then the signal to noise ratio comes out to be signal power to the noise power is 1000, and it cannot transmit at a rate faster than 30,000 bps. So you just do this calculation and you will get this particular number.